Okay, so what we have seen, we had some introduction to amortized complexity, different ways of analyzing algorithms, data structures, particularly in amortized sense. We saw some examples where the amortized complexity of an operation is much better, much smaller than the worst case, incrementing a counter and stack with multiple pop operations and so on. Then we saw that we can, if you have a data structure that can implement insert, search, insert and delete in constant time, like a hash table, we can achieve the same thing without too much loss of space, keeping the load factor of the table reasonably large. Like, we make sure that we don't waste too much space, but what we lose is the complexity becomes now amortized, because once in a while we have to copy the entire table into a new thing. So that will take too much time in the worst case, but by making sure that we do this only if the table gets filled up, and we always ask for double the space, and when the table shrinks below 1/4 of it, then we shrink it, then we ensure that the complexity is amortized. Okay. So now we are going to look at some standard versions of data structures you have seen, where we will design for keeping in mind the amortized complexity. Okay. So the data structure which we are going to design is for this priority queue operations. In the first lecture, I was mentioning about where you want to support insert, search and delete queries, and they are called dictionary operations, and the standard way to do them in logarithmic time is using some balanced binary search trees, right. Whereas in priority queue, you are not so much worried about search, but what you want to do is that you have objects coming in and you want to insert. The only thing is that each object has some priority associated with it, some number, some weight, and we want to delete the highest priority element and assign it to your printer or CPU or something, right. Typically, these are the operations you want to perform, and such operations are called priority queue operations. Okay. So there are standard data structure to do it, but so before that, suppose I care about, let's say, not this so much, but I care about insert and just the max. Okay. So my two queries are, some objects are coming in with some value, and occasionally what I would want is give me the max value. Okay. What kind of data structure would you use? How would you implement? So a typical data structure problem is you are given a set of objects where you want to maintain something, some queries. Okay. And so you pre-process your objects and maintain certain invariants on them and answer the queries. So you have some algorithm for your operations, and we care about pre-processing time occasionally, but we care more about the time for the queries. Okay. So suppose I care about the queries I'm going to ask you is insert and give me the max. How would you want to implement it? By binary tree or binary search tree you meant, right? Okay. So binary search tree. Okay. And max heap. So binary search trees can do these operations, because we already saw in balanced binary search tree, right? Not just any good old binary search trees, because if it's not balanced, then it can degenerate into a linked list. A balanced binary search tree can support this in logarithmic time, and find max would be, how would you find the max in a balance? The rightmost, follow through the rightmost thing and whatever value, because it's organized in a way that anything to the right is larger than the node, and anything to the left is smaller. Okay. So balanced binary search trees could support this in order log n time. max heap. I will tell you out about it. Not everybody may be aware of it because I know there are some mixed backgrounds. But anything else? Can you think of some simple ways? Yeah, exactly. Why do you want to complicate this? Okay, so his suggestion is just maintain the max. We've been through this. Maintain the max, right? So what do? I keep giving you objects. Throw away everything. I don't. Just remember your current max. Your data structure is one cell. Right? And a new element comes. What do? Compare with this max. If that is smaller, throw this away and keep that. Otherwise, move on. Right? And how much time for insert? How much time for max? Constant time, right? Because you're not keeping anything. So what's the moral of the story? Don't think too complicated if I'm asking you for this simple query, right? Just want to insert and I'm going to ask you max. Just maintain the max, right? Okay. Would that work if I actually also delete the max? So now I augment my query set and said I'm not just going to do insert and asking you for max, but occasionally I will also say delete the max. Then this won't work, right? Because you have not stored anything. If you delete the max, then you have to maintain this invariant, you have to fill up this cell. You don't know, so you have to. So what would you do? The usual suggestion is maintain the max and the second max. Okay, she's laughing. She doesn't like the suggestion. Why not? What's the problem with this suggestion? Right. One suggestion is just maintain the max and second max. Why is it not good enough? Why two delete? Just one delete. If I delete the max, this goes away. This gets filled up. But to maintain the invariant, you need to fill this cell, and where are you going to get the elements from, right? Okay, maintain the third max. I'll keep it sorted. This is the usual giving up solution. If you keep it sorted, would you keep it a sorted array or a sorted linked list? Right? Why? Because if you keep it sorted array, how much time insert will take? It's going to take you a whole linear time because you can do binary search, but you have to keep pushing elements. If you use linked list, we saw this again because you can't simply do binary search. I don't need to do binary search because I'm not asking for search. No, but if I want to maintain it sorted, then you have to find the correct position to insert this element. So all this is gone. So there's a very nice elegant data structure. Of course, you can do. I mean, if I care only about logarithmic time, this is a good enough solution. A balanced binary search tree is good. It can do insert, delete max, find max, and can do a lot more of things. But if I care only about priority queue operation, this max heap is a very elegant data structure which can support this in logarithmic time. But what is the advantage of it over a binary search tree? We will address that question after I tell you about the heap. So how does max heap work? So it's again a binary tree, but it's a complete binary tree, right? Which means that you keep filling up level by level. Okay, these are some things which you have already seen, know. So I'm just refreshing, right? So that's how it works. And so there is a structural constraint, and then there is a constraint on the values you place on the nodes. The structural constraint is that it's a complete binary tree. And the constraint on the values, that value at a node, it's a max heap, so it's greater than or equal to value at its children. Okay, so okay, so this would be a max heap where It's a complete binary tree structurally, and for any node, the value of the node is larger than or equal to its children. Okay. Okay, so this is the sort of the invariant, right? I want to keep using this word invariant, which is very useful. So this is what we will maintain it. So now, when a new element comes, how do I insert it into this heap? Let's to maintain the structural thing, I should insert the new element here. Let's say some 17 is I want to insert. I'll insert it here because just to maintain the structure first, and then I worry about the other property, right? So what is violated here is this is violated, this constraint. So what do you do? How do you fix it? So first, how do you realize that you have violated it? You compare it with your parent, and you know that this is larger. And how do you fix it? Swap this pair. 17 goes here, compare it with the parent, and looks okay, and you're done. Right? Now, how much time does it take in the worst case? Why? So why did I want to maintain it as a complete binary tree? Because the height of such a tree is log of the number of nodes in the tree. Right? This is a little lemma, discrete math. So if you have a complete big, one way to easily prove it is there are number of nodes here is 1, number of nodes at the level, next level is 2, 2 squared, 2 cubed, and so on. So you just sum them up and then argue that if the number of nodes is n, the height would be at most log n minus 1, whatever, something. So precisely how many comparisons you are making is exactly 1 at every level, because you just compare it with your parent. That's all you're doing at every node, and you fix it. So that's going to be in log n times you can insert a new element into this binary heap. And if I want to support this delete max operation, what do you do? So delete this max, because max is at the root, and to fix the structure property, take the last element and put it here. Okay. So you have a complete binary tree properties maintained, but then there will be some violations, you need to fix it. So 17 comes here, this goes away. Now you compare it with the children and you need to swap. So which child would you want to swap with? The greater child, because then the violation will be in one side of the tree only, right? Because if you swap with this way, then there is going to be still a violation here. Right. So compare it with the children and swap it with the larger child. So 43 comes here and 17 comes here. So I don't have to worry about this side, because this is larger than what it was, and which is larger than this anyway. So then you trickle down this violation every time you are making two comparisons at every level. Right. Compare the children and compare it with the parent. So 2 log n many comparisons and log n many swaps. Okay. So now I have given you a couple of problems asking you, okay, can you improve this 2 log n to something better, log n plus something. That's pretty interesting and challenging. If you already have well versed with this, that's a nice challenging problem to think about. Can you improve the running time from 2 log n to log n plus log n, log n plus log n, and so on and so forth. Okay. And the other question I had was, instead of binary heap, what if you had k-array heap, or how much time these things take. Okay. These are just some examples to just go and get your concept of how to do these insertions in delete max in a heap. Okay. So why is this better than, okay, binary search tree? What is, if binary search tree can do whatever, all of this, what's a nice thing about heap? Anybody has a quick find max is constant. Okay, that's one example, one reason, that because find max in a binary search tree you have to go all the way, and it could be log n. Okay, what else? What were you saying? You don't have to balance it. It is simple to implement. You don't have to balance it. Yes. More importantly, you can do everything in a simple array. You don't need these pointers. So if you read these nodes level by level, so I can write this whole heap like this. no pointers, nothing, you can maintain an entire heap in an array. And so, how will you figure out this parent and child relation? 2i and 2i plus 1. So, if I am at position I, let us say 3, its children are in position 6 and 7, there is no 18 at all, there is, its children are in position 6 and 7, right. So, using this, I mean, what are these pointers helping you to know, go to your left child, right child, parent kind of thing, but you do not need any of this, simply use them in an array, so that I can still navigate, go to my child in by just doing some multiplication of the indices. Similarly, I can go to my parent by doing a division. So, if you are one of those who do not like pointers, most people, at least the beginning programmers, do not like pointers. Nice thing is that you can represent the entire heap in an array. Not just represent, you can do insertion, delete max in an array, right, because if you want to insert, just insert it at the last position, find its parent, check for violation, swap. Similarly, if you want to delete max, delete it, take the last y, put it here, trickle down the violation, everything can be done in an array, right. Also, what another application of heaps? Heap sort. Yeah, you can sort, right. Given an arbitrary array of n numbers, you want to sort. So, what do? Build a heap. Yeah, first thing you have to build a heap. I haven't talked about it. That is something you can do in linear time, right. Let me just check this out. When I say exercise, I mean this is something you are supposed to know. I mean, it's there in books and so on. Right. Given an arbitrary array, and I want to reorder them so that the array forms heap ordered. What does heap ordered mean? It should satisfy this condition, right. Value of a node is greater than or equal to value of its children, or a value at a position I must be greater than or equal to values at 2i and 2i plus 1, because they are the children. So, given an arbitrary array of n numbers, you want to reorganize them so that it satisfies the heap property. You can do it in linear time. After you do this, then what do you do to sort? So, build a heap and then delete max, right. You do delete max operation, the max will come to the end. Another delete max operation, the max will come to the end, at the end of it. So, you do some n minus 1 or n delete max operation, the array will be sorted, right. It will take n log n time, and what is nice about it is this is one of the in place sort, meaning you can sort using no extra space, right. A constant right. Another popular n log n sorting algorithm is merge sort, but then you want to to copy your two arrays, you want to merge them, you usually use an auxiliary array of size proportional to n by 2, and there are in place versions of merge sort, in place versions of pretty much all the known algorithms, but they are a lot more complicated. But this is a very nice, elegant in place n log n sorting algorithm, right. Given an array, build a heap, do n delete maxes, and since the heap can be represented in an array and all these operations can be performed without more than a constant extra space, you can sort. Okay, good. So, this is a quick revision of heaps and their uses. And so, if I want to search for an element in heap, how much time will it take? What will you do? So, given some query element x, I want to know whether x is in the array. It could be as bad as n, because this is not a structure set up for search, right. This is one of the disadvantages of heap, right. I mean, between balanced binary search trees and max heap, softmax heap, heap is very simple, nice and easy to implement, but it can only support these priority queue operations. But if you want to support in particular the search operation, you can't. I mean, you can do in linear time. I mean, okay. Okay. Another popular operation which you will come across in when you are trying to use heap for any algorithm you have used heap. Can you recall some popular graph algorithms? Minimum spanning tree, yeah. Shortest path, Dijkstra's shortest paths algorithm, Prim's minimum spanning tree. I'll revise them. Maybe let me do that now. Let's say anyone. Let's do Dijkstra's shortest path, right? So it's a single source. So you have a directed graph, weights on the edges, non-negative weights on the edges, and a specific vertex source. The goal is to find the shortest path from S to every other vertex, right? So how does the Dijkstra shortest path algorithm work? What is the invariant you maintain at any point of time? Or just tell me the algorithm if you remember. Forget the invariant thing. Okay. So how does the algorithm work? It's sort of a greedy algorithm. How does it work? Experts. Forgot. Mm-hmm. Yeah. So the invariant it maintains is at any point of time, I know the shortest path from S to some set of vertices. Okay. So let's call this S. Shortest path from S to vertices in S have been computed. Okay. So what is left is some V minus S. And the other invariant to maintain here is some number D, which is, let's call this V, length of the shortest path from S to V, but you are allowed to use only vertices in S. So at every point of time, the algorithm maintains this invariant, right? What is capital S when you start with? Yes, little s, right? Because I know the shortest path from little s to little s, 0. So I know that. So S is then the algorithm goes through a loop. So and what are these D values? Well, the length of the direct edge from little s to V, that will be the D values. Wherever S is not adjacent to, they will be infinity. Okay. Then the algorithm says delete the smallest from here, take that vertex, add it here, right. So there is a little proof which tells you that for that vertex, the smallest D vertex, that is the shortest path. You add it here. Now I have one extra vertex to V, so I may have to update these D values, because through this little V maybe I get something shorter for these vertices. So I look at the neighbors of V and you will do some adjustment, right. So, okay, since I started, let me actually write the algorithm. So, when how long would you continue this? As long as if S has gotten every vertex, then you will stop, right? As long as that doesn't happen, let U be a vertex in V minus S with the smallest D value, right. So, delete so my S becomes S union this U. So, automatically V minus S becomes V minus S minus this vertex. Now, some new vertex has come here. So, I will look for its neighbors and see whether okay. Also, every vertex here also has a D value, which is actually the length of the shortest path from S to that vertex, right. For V in the neighborhood of U, if du plus the cost of uv is less than dv, then this is it. This is the entire algorithm. Okay. So, what am I doing? For every neighbor, my notations are okay. So, if this is a vertex which is a neighbor of u and there was a d value stored here, and I check whether through u I get a shorter path, right. How do I know that? It is du, which is the length of the shortest path to u, plus this edge uv. If that is less than whatever was stored before, which is dv, then I update dv by this new value. That is it. And do this for every vertex adjacent to you and repeat, right. So, I do not have to say this, but so this is the entire Dijkstra's algorithm, and presumably you should have seen the correctness of this algorithm. If not, please go check. Why is it correct? So, it is sort of a greedy algorithm. It with a simple loop, it finds the shortest path length. It actually finds the shortest path length. The final d values will be the shortest path length, but you will also get the shortest path because you just remember whenever some d value is updated, you remember who was my previous vertex which caused this update, then you can sort of retract the path itself at the end. Okay, so now let us look at what are the queries involved and what sort of data structure is appropriate to implement this, right. So, if I want to translate this into a program and come up with appropriate data structures to implement, let us see what is happening. So, in the first step, you are looking, so you have a bunch of numbers and you are looking for the smallest, right. That smallest number is actually deleted from that set, added somewhere. So, you are doing something like a delete min. Okay. And then what is happening here? Certain values are changed, right, because you look at the neighbor. So, this is a set of numbers you are trying to maintain, and from this you will delete the smallest, do something, and then certain numbers are changed. In particular, they are decreased, right, because otherwise I won't change. So, the two operations I want to maintain are delete min, decrease value. So, I have an array of numbers and repeatedly the queries I am asking is take the minimum. So, delete min, and then I just go and say, oh, whatever this value is, bring it down to 17, this comes down to 11, this becomes 23. Okay. Now, do a delete min to this decrease key, that is what is happening. So, okay. The entire Dijkstra's algorithm, after the correctness is checked, and if you really want to implement it, what kind of queries you want to perform these operations. You want to delete min and do some decrease values, right. So, in particular, this is important, when I want to do some decrease values, I will point to those values, right. You do not have to search. I am not going to say wherever 35 is, go and please change it to 17. No, that's hard. Remember, if you are trying to use heap, I can't go and find out where 35 is very fast, because that's a search operation. So, it's very important that when you implement Dijkstra's algorithm, and if anybody has actually implemented, you should have paid attention to this, that you should also know where that particular value is, and I am going to change it. Okay. Okay, good. So, now can I do this in a heap, decrease value? How would I do it? In logarithmic time. So, I want to go, okay, delete min we already saw, we can use a min heap, but if I also want to support this decrease key operation, how can I do? Exactly. So, I have this heap maintained, I am pointing to this value and say change, decrease it, it is a min heap. So, when I decrease it, none of its, if it was smaller than its children, it will continue to remain smaller than its children, because it has become smaller now. So, only violation it can have is with the parent. So, compare it with the parent and do some swaps and in logarithmic time. Okay. Another simple black box answer is delete the old value and insert the new value. Okay. But then we did not really see delete operation in a heap, but that the same way you can do it. Take the last value, put it wherever you want to delete and do the adjustment. So, you can do these operations in logarithmic time using a standard binary heap. Now, how many delete min operations you are doing for Dijkstra's algorithm? Let us say my graph is this. If this is, there are n vertices and m edges, how many delete min operations do you do? Yeah, including s. So, n minus 1, right, because s is sitting there. So, you do n minus 1 delete operation, and in the worst case, how many decrease key operations you might do? Well, it is here, the whole program is here, right. I have it here. This is where decrease key operation happens. How many? M, why? So, just degree in the loop, how many times you do it in one loop, it is just the degree of that vertex in the worst case, right. So, summation degree, right. So, is it 2m or m? Oh, I meant order m, so it does not matter. No, let us be more precise here. Actually, m is correct, because see the degree of the vertex. So, if I look at the degree of vertex, there are also edges here, which I am not considering, right. So, really edges are only counted once, because once that vertex comes in, you are only looking at edges outside. Okay, so, you are doing, okay, if you are happy with, we go anyway. So, this whole thing will take, so it is basically, so this is the runtime for Dijkstra's algorithm if we use simple binary heap. Okay. But here again is something to look at, that I mean this is an example where I said, when I motivated amortized complexity, I said often you may not care about worst case query for one operation, because you are not doing one operation. When I use it in some graph algorithm, I am doing a sequence of operations. So, in particular, I am doing this m decrease keys and n delete mins. So, somehow if I have an amortized better time for this, right. So, in the worst, one decrease key may take a long time, but if I can do a sequence of decrease key operations faster, I will be able to improve the runtime. Okay. So, we will march towards such a data structure where the goal is to improve the amortized complexity of these operations. In particular, we will see that we can improve the amortized complexity of decrease key to a constant. Okay. So, and the data structure that is going to achieve this is what are called Fibonacci heaps, but we will get there probably next time, but I am going to just sort of do some warm up and do a different. So, one other operation which, okay, so we will do what is called the binomial heap. So, in particular, one other feature which might be useful is that if I have two heaps of different sizes and somehow I want to merge them and build one big heap, can we do it fast is one of the, it's called mergeable heap, and you can think about it and see that binary heaps are not very useful for that. Right? If I have two binary heaps and I just want to merge them and get one big binary heap, which is the union of these two things, not so easy. Okay. But binomial heaps you can do it. Okay. So, let me just define this. So, first we will define what is called a binomial tree. It comes with some order I. Okay. I denotes the degree of the root. Is defined like this inductively. B0 is just a tree with single node. Okay. And if you already defined Bi, what is Bi plus 1? Take two Bi. So, this is a Bi, another Bi. Make the root of one Bi the child of the root of the other. Okay. This is a binomial tree of order I. So, how does B1 look like? So, this is B0, B1 would be like this. Okay. I mean either this side or that side. So, it could be, how does B2 look like? So, take, that is B2. Okay. B3 would be and so on. Okay. Let us quickly write down some interesting properties, right. Number of nodes in Bi. How many nodes are there? 2 to the power I, right? How do you prove it? Well, BIs are defined inductively, so natural way to prove this is by induction, right? Because you just take 2 BI minus 1 and you are, that's the number of nodes, so 2 power I. Okay. All this thing will be useful when we actually get to binomial heap. Number of nodes in level I. Okay, so root is at level 0. So let me just, in BK. Let's do some example, right? What is B3? Number of nodes in level 0 is 1, in level 1 is 3, right? These 3 nodes. In level 2 is this, and this is level 3. Have you seen this pattern? Right? For B2, it is 1 to 1. Binomial numbers. So, number of nodes in level I in BK it's K choose I, right? How do you prove it? Induction, right? Because what is this number at level I? Well, so you have this a BI minus 1 and BK minus 1 and BK minus 1, and who are all the nodes in level I? The level I nodes here and level I minus 1 nodes here, because it just gets you one level. So, by induction it is K minus 1 choose I plus K minus 1 choose I minus 1. That is exactly K minus 1, K choose I, right? And that is why these are called binomial trees actually. So, we quickly went through, but let me just say, if you didn't follow online, basically just try induction. It's a good, nice, simple exercise. Okay, the subtrees rooted at the children of the root okay, just parse the sentence first. So, what am I saying? Look at the root of BK and look at its children, right? Each child is a root of a subtree, right? Can you say something about these subtrees, right? So, what am I saying? So, look at, this is the root of B3, and if you look at its children, the subtrees are, these are the subtrees. Yes, they are B0, B1 up to BK minus 1. Okay. Again, this is not, I mean, I just gave you an example, but you can prove by induction. Very simple example, right? Very simple proof, right? Because if you look at BK, it's just a combination of 2 BK minus 1. So, in this BK minus 1, you have B0 to BK minus 2, and then the other BK minus 1. Okay. So, it's not even simple, it's actually a trivial proof, right? Okay, good. Do I need anything else? Well, we will see. Okay. So, I have just defined you what is a binomial tree, and I have not told you what a binomial heap is. Before that, I will define what is a binomial queue. This is a collection of binomial trees. So, it is a set. Such that for any I, there is at most one bi. Right. So, I could have a binomial q could be B0, B7, B11. Okay. So, it will be, I mean, it is basically a tree which has B0 as one node, and B0 will be looking like something, and it will be B11. So, this set, this collection of trees is what I called a binomial Q. The only thing I want is that I cannot have 2 B5s or 2 B7s or 3 B8s and so on. For any I, at most one BI is there. Okay. Here is an interesting next property. For any n, there is a unique binomial Q with a total of n nodes. Note that you do not have a binomial, and if I want a binomial tree with 17 nodes, you can't get it, because binomial trees have the number of nodes is 2 power I. So, you can only have powers of 2, but binomial Q is a collection of binomial trees. Now, if you give me any n, I claim that there is a unique binomial, when I say unique, it is up to these isomorphisms, these structures. Why is that and how? Exactly. So, how will you get this? Take n, write it in binary, wherever there is a 1, pick that bi. In that position, wherever that position is I, if the ith position is 1, you add bi into this, right. Then that is the binomial Q with total number of nodes, and it is unique because for any n there is a unique binary representation, right, because the number of nodes. So, if I have a binomial Q with some bi1, bi2 and bil, then the number of nodes in this tree would be 2 power I1 plus 2 power I2 plus blah blah. So, if I want n as a powers of 2, n as a sum of powers of 2, what you do is just take your binary representation. Okay. Now, what is a binomial heap? Well, it is a binomial Q. Now, I am going to throw in values on the nodes, and each tree in the binomial Q will have a heap order. The value at the parent is less than or equal to value at its children. If you want a min heap, otherwise you do a max heap, value must be greater than or equal to its children, right. So, binomial heap, so structurally it is a binomial Q with values at nodes So, what is a binomial queue? It's just a collection of trees. So, for example, I might have, so this is a binomial queue with 1 plus 2 plus 4, 7 nodes. So, in general, a binomial queue is just a collection of binomial trees. Some, so here it's B0, B1 and B2, but I might just have a B0, B3, B11, B23, and that will be a binomial queue. And the number of nodes in the binomial queue is 2 power 0 plus 2 cubed plus, this will be the number of nodes. Now, all I am saying is, if I want a binomial queue with some n nodes, write n in binary, and wherever there is a 1, if ith position has a 1, just pick a bi. Then you know that the sum of these powers of 2 is exactly n, and since n can be written uniquely as a binary representation, you will have this unique set of binomial trees where the total number of nodes is your desired n. Okay. So, under binomial heap, structurally it is a binomial queue. Now, we will have values on the nodes satisfying your min heap or max heap property. Okay, so whatever. So, if it is a min binomial heap, then it will satisfy the min heap property. So, it is a collection of binomial trees. Your values which you want to represent are all distributed on the nodes of these trees, and each of these individual binomial trees, there is a parent child relationship like a heap, like a binary heap. Okay, so one thing I am not going to spend time on, and how do you implement a binomial heap, right? Because the degree of a node is not a constant, it can vary, and you have to represent the children in some order, because we're going to access these children in some particular order. So, but using some heavy duty pointer implementation, you can represent this entire, and you also link the roots of these nodes. And if you are looking at a min binomial heap, you also remember the min or the root containing min. Right? Clearly, the min element is one of the roots. If you are representing each tree as a min heap, so you also remember which thing has the root, because it helps on some of your operations. We will see when we get to the operations. If it's necessary, we will link them. Okay. But abstractly, it's just a collection of trees, each tree satisfying some heap property. Okay. So that's a binomial heap, right? So like we have seen binary heap, we're just complete binary tree. Oh, so let's now write down one more property which will be useful. Is how many trees are there? Number of trees in a binomial heap with n nodes log n, because it's just the binary representation, right? How many bits are in your binary representation of n, right? So it's at most log n. And what is the height of any tree in a binomial heap? Well, remember, or basically height is the same as the order. Oh, this is something else. We didn't, should have written it. What is the height of bi? I, right? And so what is the maximum order I you can have in a binomial heap on n nodes? Log n, right? So that's also at most log n. These are some useful properties when we get to implementing our queries or operations. Good. So all of this now, you know what a binomial heap is? It's a collection of binomial trees, and the values are stored in the nodes in heap order. Now let's get to the queries we want to support, right? So if I want to find the min in a binomial heap, how much time will it take? Constant time, because I've actually stored it, right? I've stored it. Can I erase? Okay, so find min. Constant time because it's stored. If you didn't store the min, then you just have to check the roots. There can be at most log n of them, so it will take log n time. How much time will it take to insert an element? How would you insert? So let's assume that, okay, there can be duplicates, okay. So how do I insert it? Well, what if I just go into one of the BIs and insert it like I would insert in a binary heap? Right? How is my tree looking like? So it's some B1, B7, B11, B15, right? So I just go to B7, insert it as a leaf, compare it with its parent, do some swaps and fix things, in log n time I insert. Is that fine? Yeah, it won't be a binomial tree, right? My binomial heap is just a collection of binomial trees, and each binomial tree has a power of 2 number of nodes, right? If it's a degree I, then it has exactly 2 power I nodes. So you can't do it this way. You will, the invariant won't be maintained, right? Okay. So how do you insert? Create a B0 with this node, right? So what is it? So I want to insert X, let's say in my binomial heap B, create a B0 with X. Okay, so what, I mean, I already have a collection of trees here. So I just go create and put X here and add it to this list. We are not done yet. Why not? If there is already a B0, then remember in our definition of binomial Q, we said for any I there can be at most one BI, right? If in my Q already there is a B0 sitting there, then I violated that, so I have to go somehow fix it. How do I fix it? Yeah, so if I have another B0 sitting here, then I can link these two nodes and create a B1, right? So I can do this, or I can do this. Which should I do? But it's a min heap property, each tree. So whichever is smaller guy, make sure that's a root, and so link it and make it into a B1, right? Am I done? No. There may be another B1 sitting there. So then link those two B1s in the same way. Basically, you just have to compare the roots. There's nothing else you have to do, and figure out which root should become the child of which root. And so you create a B2. There may be another B2 sitting there, you have to fix all that. So in the worst case, it could be log n worst case. Why log n worst case? Because of property phi. Right? Number of trees in my binomial heap is at most log n. So you may have to just go and do this operation. But in the amortized time, can anyone see this? That it's faster. Same as the, it's same as the counter increment we saw, right? So what is happening here is that you have a binary representation of a number. I'm adding 1, right? Okay, and this, if there is a 2 ones, what do? You make it a 0 and add 1 to the next guy. That's exactly what's happening, right? So in the worst case, it could be the number of bits in your binary representation. But if you start with an empty binomial heap and do a sequence of n insertions, then it will be constant amortized. Okay. So now you're going to see a lot of resemblance to binary counter here. So why is this log n worst case? By property phi. So the algorithm would be, if there is already a B0, merge to get to B1. If there is a B1, merge to get B2, and so on. Right? So the worst case log n, but is order amortized, constant amortized, because as in incrementing a binary counter. Okay, let's do decrease key operation. How would you do and how much time? So this is good. Already we are seeing improvement in binary. Where will you get such entertainment? So how will you do this? What is the point operation? I want to point to a node x, which has value x, and I'm saying change that to y. In particular, I'm decreasing it to y. And how much time and how would you do? Log n time. Okay. Why? How would you do? Yeah. So you can it's just a local restructuring in the same tree, right? Just like you would do it in a binary heap, here it will work because you are not changing. N doesn't change. The number of values remains the same. One particular value is decreased. So compare it with its parent or children and do your fixes in log n time, because the height of any tree in a binomial heap on n nodes is log n. So it just time proportional to the height of the tree. So restructure, not even structure, right? Swap values in the so it's log n worst case. let's do merging of two heaps, two binomial heaps. I want to merge them. Right? So I have this one tree which contains, I shouldn't give them name. Yeah, H1 needs to B. I've reserved it for Bi. So H1 may be like something. And I want to merge them together into one big binomial heap. Okay. I mean, elements repeating is not a problem. You know, there are like different keys. So how would you merge? Take the unions. Take the two mins. Okay. First, you also need a min. So take the two mins, compare and update the min. And now I'm just going to my new H is basically I'm going to do H1 union H2. Right? And then there will be some violations I need to fix. Okay, so you know I've drawn B0, but they're like a physical tree sitting there with values on the nodes. So what I'll do is just make it a big, huge collection. Assume that they are actually ordered in the increasing order of the BIs. I have this big, huge collection, and that's my new binomial heap, which contains the number of nodes, same as the total number of nodes. The min heap property is all satisfied in each tree. The only other thing that will be violated would be that in this union, I may have two copies of the same BIs. But whenever I have two copies of the same BI, I know how to deal with them, right? Just link, pick the min of the roots, make one the child of the other, and you will make a BI plus 1. There may be another BI plus 1, link them, so on. Okay? So, how much time in the worst case? Right? Suppose this has n1 values and this was n2 values. You know, it's at most so. And then fix the BI violations. Right? By linking them. So there may be log n1 many trees here, log n2 many trees here. So max of these, or log n1 plus log n2 many trees, right? So worst case. More importantly, you can do it in logarithmic time, right? Remember, in a binary heap, I have a binary heap on n1 nodes, binary heap on n2 nodes, and the best way to merge is, you know, linear. Now, what is the other operation we want to support? What's the other priority queue operation? Delete min, right? Insert and delete min are the two key operations we wanted to do. So delete min, how would you do? So min is sitting in one of the trees. I'm going to delete that root. This is going to be useful here. This property is going to be useful because so that will be one heap, and my original thing is another heap. I'm going to merge these two heaps, right? So let's do. Okay, so let Bi the tree whose root is min. Of your you're given this binary heap, a binomial heap H, where I want to delete, then so delete the root from property 3 its children form a binomial heap H1 is equal to B0, B1, Bi minus 1. Because the children are exactly B0, B1, Bi minus 1, and they form a binomial heap because each tree has nodes of satisfying heap order and at most one of each order, all that is fine. So now merge, we know how to merge. Right, so and we have seen that this takes log n1 plus log n2, so it's I is at most log n, so number of children is at most log n minus 1, and you have to find their roots, find the min, so all that. I'm going to just say on log. Good, so what we have achieved is whatever we can do in binomial heap, binary heap, which is essentially insert and delete min and decrease key in the same time. Plus, we can also do merge in logarithmic time here. Okay, we still haven't yet achieved our goal of supporting this operation in constant amortized time. Because remember, this was our goal to speed up Dijkstra's algorithm or Prim's minimum spanning tree algorithm. Okay, so the idea suggested in Fibonacci heap to implement decrease key is as follows. So Fibonacci heaps is exactly as, okay, I'm not going to define what a Fibonacci heap is because there is no such clean definition like what we have for binomial heap. But we are going to do decrease key in a slightly different fashion. And whatever collection of trees you are going to get along the way is called Fibonacci heap. Okay. So how are you going to do decrease key? So remember, so you have a tree. It's not just binary because you can have multiple children. And decrease key operation is told, change this value, so decrease this value, right? This is what decrease key operation is defined. You have to tell me which node the value is because you can't search for it. So what we will do is as follows. We are going to cut this subtree and add it to our collection. Okay. So it's like a constant time operation, because you tell me this key I have to. I'm not going to go up and down checking for a violation and so on. I will just cut this subtree and add it to my collection. Okay, it's a constant time operation. But what? It's no longer a binomial tree. You've taken a binomial tree and you've cut it in some arbitrary fashion. So all the nice properties we have proved, we have to rework them out carefully, right? There is also other problem that you may have this huge tree, and I have done all kinds of cut so that it becomes a big chain. So the height is not logarithm in the number of nodes, all kinds of, and this is one real problem we need to deal with. If I just do, you have to decrease key, I cut it and add it to my collection. There may be lots of problems, in particular we need to rework all the nice properties we proved. But one problem one can immediately see is that if I'm doing all kinds of cuts, then one of the trees can just become a huge chain of some I nodes. So the height is no longer log I. Okay, so we need to deal with that. So the way they deal with is, I'm not going to do all kinds of arbitrary cuts. I make sure that, okay, so let me just, one more thing we'll do is make sure that each node loses at most one child. How do I ensure that? Well, what do I mean? So this is asked to decrease the value, and I'm going to cut it and put it here. Now later on, I'm going to come here and say, okay, change this value and decrease the value. I don't want to cut this. If I'm forced to cut this, what we'll do is we'll cut the parent and create a new subtree, add it to our collection. Okay, so this is a cascading cut, right? So we'll do all this, little more detail and do careful analysis tomorrow if that happens. But I just want to give you an idea of what that happens. Cut the subtree rooted at its parent and add it to the collection. Essentially, that's all is Fibonacci heaps, right? It's basically, you start with some empty trees, collection of trees, and insertion happens. Just do as you would do in a binomial heap. When delete min or a decrease key, anything happens, just do as, except for decrease key, we will implement them differently. We will just cut the subtree and add it to the collection. But if its parent has already lost one child, then cut the whole parent and add it to the collection. But its parent might have lost another child, cut that, there is cascading cut. So in the worst case, a decrease key operation may take logarithmic time. But can you think of a way you can amortize this? Because, right, here is a very simple way to amortize, right? So when I'm doing this cut, first cut, I give this guy some extra credit to give its parent, to say that somebody will cut my sibling. At that time, you're going to lose yourself. So use this credit to pay for your thing, right? So we will argue that with constant amortized time you can implement this, because this cascading cut happens very rarely. If the cascading cut happens, mean that the parent has lost another child, so I would distribute this cost to the first child, which is being cut. Okay, so we can argue. First thing we'll argue is the decrease key actually, by this, with some appropriate credit, will actually take constant amortized time. But the serious problem is that or the hard work we need to show is that the height of the tree will remain still, any of these trees will remain logarithmic. The number of trees is going to blow up now because, if you're going to add every decrease key may just cut the subtree and add it, and we use the fact that the number of trees is log n. That's going to be off, and we need to deal with that. But the number of trees is really not a problem, because where did we use? Whenever we were linking things, right? There will be some cleanup operation done by some operation which is going to link two of these trees, and there we use that, maximum there are log n many trees, so you'll spend log n time. But that's not a problem, because with every tree we'll put some credit, right? Whoever created the tree will come and give some credit to it, which will be used for linking. Okay, so the number of trees won't be a problem. The cascading cut will happen rarely. The decrease key will be constant amortized time. But the hard work is to show that the height of the tree will be logarithmic, and that we will show simply because we are not just arbitrarily cutting. You are allowing only one for each one. One child is getting lost. So that's sort of a carefully chosen set of cut. We will show that the height will be not log n, but log n to the base what? The Fibonacci phi ratio, and that's how this number will, it's called Fibonacci number. Okay, so all this we will show tomorrow, and the main thing we will achieve is that decrease key can be supported in constant amortized time, still maintaining the worst case time for every other operation, and as a consequence, this Dijkstra's algorithm, Prim's algorithm will have better running time, right? So this is the important thing is the algorithms are the same. We will just use some better data structure, in particular look at this amortized complexity to argue better implementation of the same algorithm. Okay, tomorrow.